So today we're going to do nonlinear models, still first order differential equations because those are the only things that we can solve. Um, but the examples that we took a look at last time all were linear differential equations, first order linear. So you always have a method for solving for them, and that's usually the integrating factors. But if for some reason those linear models happen to be separable, then you probably want to do it that way. Here for nonlinear models, it just means it's not linear, but you can still solve for it using either, if it's separable, you can use separable differential equations, or if it's one of those other forms that we might have ran into, like the Bernoulli or homogeneous or whatever, then you can use any of those other methods. Most of these examples that we're going to look at, though, are separable, so it's just a matter of you being able to integrate uh, correctly. And I think I already told you how I felt about integrals. I think you should be able to do a bunch of different types of integrals. On the test, you get a whole, sheet, back, front, sheet of notes. So if you feel rusty with your integration, you may want to include some integral formulas there. And I hope you know how to use integral formulas so that you can do things a little bit quicker than just, having to go through the process of, oh, am I going to have to use trig substitution here, or is this going to be some partial fractions or whatever? So we want to be able to have you go through the integration rather quickly instead of getting stuck on something that some integral that you might have forgotten how to solve. So let's take a look at a first example of a nonlinear model would be the logistic equation. So it's similar to kind of Newton's law of cooling, except there's a P. Do you guys know what logistic equations look like graphically? They use logistic equations in general to do population growth. And when we first talk about population growth, we think of an exponential function. Okay, so that makes sense to have population growth being modeled by an exponential function. But if you look at, a petri dish with bacteria growing in it, for example, that petri dish is only so big, right? And the bacteria growing in it will have a limit to it. We can take a look at a population in a country also. A population in a country can keep growing exponentially, but at some point it has to reach a limit. And so the whole idea of an exponential growth might make sense in the beginning, but in the long run, it's not going to make sense anymore. Population on Earth. Earth is only so big, right? It seems like you keep growing and growing, but Earth has a finite amount of space, and eventually it'll reach a limit. So a logistic equation will allow you to have a limit for your exponential growth. So here's an example. It says here the number of supermarkets throughout the country that use some sort of computerized checkout system is described by initial value problem. So here they give you the initial value. So that's kind of nice. Nice if they do that. So really all you're doing is solving for it. But a lot of times in this section, your task is to model it. So your task is to come up with this differential equation before you solve it. So I'm not sure how I'm going to test you on that yet. I might go back to the techniques in chapter 3 where they just tell you to set up the equation and not solve it, because I'll probably give you other things to solve anyways. So we have dn dt is equal to n times 1 minus 0.0005 n, and then we have an initial condition at 0, it's going to be equal to 1. So the interesting thing about this is that this is a what's this called? A dn dt is equal to that. What kind of differential equation is that? What kind of differential equation is it when you only have the dependent variable involved and not the independent variable? What? This is called an autonomous differential equation. And with autonomous differential equations, you can do a phase portrait for it. So that's what they have. So part A, they're asking us to use a phase portrait concept to predict how many supermarkets are expected to adapt the new procedure over a long period of time, and then by hand sketch the solution curve of the given initial value problem. And then they want us to solve for it, and then they want us to figure out how many companies are expected to adapt the new technology in 10 years. Okay, so seems pretty straightforward. Again, once you have the differential equation, the solving should be easy, right? I hope it'd be easy. So let's try it. An autonomous or a phase portrait, remember, is a one-dimensional graph, and usually we want to denote it with a vertical axis. This is an n-axis or a y-axis, whatever the dependent variable is. And what you want to do is you want to solve for when this derivative is equal to 0. Remember, this is the dn dt are the slopes. And you're saying the slope's equal to these things, and it doesn't matter what the time is. It's always going to be the slope is dependent on the n only. So if we solve for this when n 1 minus 0.0005 n is equal to 0, we have n is equal to 0 and n is equal to, what is that? What is it? N is equal to 2000. So those are your, what are they called? Equilibrium points. Yes, these are equilibrium points. So that's the first part of the phase portrait, is to figure out the equilibrium points, and then you need to figure out what's happening between around the equilibrium points to determine whether they're sinks or what are they called? Sinks or repellers? Stable, unstable, semi-stable. So the way you would do that is to take your slope, and then you put values that are less than or between or greater than equilibrium points. So if I put let's do this in a different color. If I put an n value that is, oh, let's say negative, so less than 0, so n less than 0, I'm looking below the 0. I would get a negative times a 1 minus something times a negative number. So that's basically 1 plus something, right? 1 plus something is going to be a positive. So this is going to end up being a negative. So I'm going to be, I say change colors, but you can't really tell her. I'm using green, by the way. So the first color was blue, and now I'm using green. So I'm going to get a negative. So my phase portrait below the 0 will be going down. Between 0 and 2000, will give me a positive number for the n. And then if I put a number between 0 and 2000 in there, like 1. I have 1 minus something that's going to be less than 1. So this is also going to be positive. So this is going to be a positive value, which means here I'm going to be going up. And then I will try to put in a value bigger than 2000. And so this is going to give me a positive for the first term, or the first factor. And then if I put a number bigger than 2000, then I have 1 minus another huge number. So the minus is going to dominate. So this is going to be a negative. So that's my phase portrait. It looks like 2000 is a sink, and or what do they call it, stable, and 0 is unstable. Okay. Yes. First derivative test. Yeah. Yeah. Except instead of first derivative test with a horizontal line and you're putting pluses and minus, it's a vertical line and you're making it going up or down. It is almost like the first derivative test because you're testing for the slope, as a matter of fact. So if we were to draw sample curves, I think we've had some practice in drawing sample curves where you had your independent and dependent axes. We know that 0 and 2000 are going to be asymptotes. And if we know that we are decreasing below 0, then our graphs would look like this below 0. And increasing above 2000, you know their graphs are going to look like that. But between 0 and 2000, we know that we're going to have an asymptote on the repeller side, on the unstable side, going off to negative infinity. And then we're going to have an asymptote on the positive side, approaching a stable equilibrium. So somewhere in between, you just have this thing. Of course, your initial condition tells you that when t is equal to 0, your n value is equal to 1, so it should pass through that point. Okay, so our graph, oh, I'm sorry, I made a mistake for our graphs here, huh? Yeah, these should be going down. Okay. All right, so we have a general idea of how the graph is going to look like. Let's actually solve for this differential equation and look at the graphs. So this is where we get to solve for our differential equation using some sort of calculus. This is, how would you solve for this? What technique would you use? What? Partial fractions? Well, the technique that I was looking for is like separable differential equation. You can multiply the n and then get some sort of Bernoulli equation out of this, but you know that's more work than needed. So let's consider our separable differential equation, where you have to do partial fractions. I really don't want to do this. So can I just Maybe we should have a like an integral workshop or something. Um, I'll hold an integral workshop. Yeah. Well, there's like a 1 in the numerator. No, because long division isn't going to get you anything for this, right? Like there's nothing to divide. You have a 1 on the numerator. So, all right. I would expect you to know how to do this. I'm not going to do it. You can pay me to do a workshop on integration. Or you can get your money back from your Calc 2 teacher for not teaching you. Oh, just kidding. I'm going to use Wolfram Alpha. So we're going to integrate 1 divided by n times n. So we have the log in Mathematica is like ln. It's a natural log. So we'll take that. This is partial fractions, by the way. So you that should be one of the techniques that you're expected to know to be able to do in your exam. So we have ln of n minus ln of 2000 minus n. N is between 0 and 2000, by the way, right? So we know that this is, we can eliminate the absolute values if we want. And then the dt, if you integrate the dt, that's just going to be a t with a constant. So we'll put all the constants on that side. All right. Ideally, we want to solve for this. Solve an initial value problem. Oh, let's actually solve for c. We can solve for c now by putting in our initial values and then getting a value for c. And then maybe if we have a chance, we can solve for n. So t is equal to 0, n is equal to 1. So we have ln of 1, which is 0, minus ln of 2000 minus 1 is equal to c. So c equals ln of 1999 negative. So we have ln of n minus ln of 2000 minus n is equal to t plus or minus. Okay. Let's see, should we try to solve for n? Solve initial value problems and compute how many companies are. So we can put t is equal to 10 and then solve for ln. But let's solve for n. I think this is some interesting algebra that uses a lot of logarithms. So let's yeah. Well, let's do the subtraction for. Let's bring this ln of 1999 on the other side first. So ln of n minus ln of 2000 minus n plus ln of 1999 is equal to t. And I think we can combine all this into one ln. The positive ones will be on the numerator being multiplied, 1999 n minus 2000 minus n. And then we'll take the e of both sides, 1999 n divided by 2000 minus n is equal to e to the t. Now, how do you solve for n? There's two n's there. Any ideas? Do you remember how to do this in what? So 1999 n is equal to e to the t 2000 minus n. Distribute. And then bring all the n's over to the other side. Factor out the n and divide. And then that should be plus. So now n is by itself, and then we can put in the value that we want for t. So in 10 years, you'll get the value, and then 20 years, you get the value, etc. And this will also be helpful if we try to graph it. So n of 10 is equal to 2000 e to the 10th power divided by 1999 plus e to the 10th. Anybody come up with this answer? While you guys do that, I will see if I can type in this equation. Suppose I can graph it here. Let's graph it in Desmos. What do we get? $1833.59. No, that's fine. So it's between 0 and 2000. That's good, right? It's closer to the 2000 mark than 0, so that kind of makes sense. I started to graph it, and so far my graph looks like this. That's not helpful. What do I need to do to visualize this properly? If you're doing this on your graphing calculator. By the way, you guys have a graphing calculator in case I need you to graph something on the test? All right. So how would you graph this? I mean, this is all I'm seeing in my graph. What do I need to adjust? What? The what? Zoom out. I can zoom out. That might take a while. What's a quicker way of checking a zooming thing? The window? You guys know how to do windows in your graphing calculator, right? So I want my x, well, according to the problem, I want my x to just be able to capture from 0 to 10, but I maybe go a little bit farther. So maybe instead of going all the way to -24, I don't need 24, maybe -10, and I don't need to go all the way to 60, so maybe I'll just go to 20. More importantly, the y-axis goes from some value to all the way up to 2,000, right? That's my ceiling. So if I go to 3,000, maybe that's a little too much. 2,500. That might give me a better idea of how my logistic function looks like, right? We're tracing at x is equal to 0, at t is equal to 0. My y value is at 1. And at 10, what? 33. So at t is equal to 10, I have my n, or my whatever value you call it. So if I ask you to graph something and graph some pertinent points on the test, I would expect you to graph that with this point and label the points. Okay. So you should be able to take your calculator output and be able to graph it, right? Maybe I shouldn't have done this on my graphing calculator. Do you guys have your graphing calculators with you? Did you follow along? Should we do it? So you have to know what the function looks like, of course. And you have to properly adjust the window, right? La 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 la. There you go. Oh, I think I'm in the wrong mode here. Let's mode out of that. Functions. All right, so we need to just plug in our function. Our function was, what is it, 1999 times x. That's not x. Oh, 2000? 2000 e to the x. E to the x. So there's a plus in the denominator. I probably want to use parentheses. 1999 plus. There's a shorter cut for e to, oh, there it goes. It's e to that. E to the x. So again, when you hit graph, you're not going to get anything useful here, right? So you want to adjust your window. So let's adjust our window. 40 to 40, negative 40 to 40 might be a little too much. I'm just going to go to negative 10 to 40, maybe 20. The scale tells you what the tick marks should be. So scales of 1 would probably be fine, but if you want to scales of 5, then it'll scale by 5. More importantly, the y value, right? This is where we get to see the whole thing. So let's go from like minus, maybe we can try minus 100 to 2,000, maybe a little bit past that, 2,500. And then we'll go steps of 100. Maybe steps of 100 is a little too much even. Oh, maybe it'll be good. All right, let's try to graph it. So it's still kind of hard to see. Maybe I should shrink my my x values. This is good enough, actually, but let's see. Make it look even nicer. Let's go from minus 5 to 15. I didn't notice the scale, so let's graph it again. Yeah, the scales for this is still kind of tough to see, but I think it's fine. All right, and then you can always trace when x is equal to 0, your y value is at 1. When x is equal to 10, your y value is at 1833. And if you'd graph this, you didn't have to punch all those numbers in by putting 10 into your calculator to get the output. So, okay, questions? All right. So this could be helpful. And I hope you all know how to use your calculators. Let's try another problem. I was going to have you do some group work, but do it next time. Next time, there is no next time. It's too late. Should we do this one? This is Gompertz. I don't know if that's pronounced correctly. So here's another differential equation. So what they do is they play around. The logistic model is a good model, but sometimes they need to do a little tweaking to make it more appropriate for whatever application is being used. So the Gompertz model is used in more accurate population depictions of things, and sometimes, at least I read it in the book, they use it in some actuarial science where they have to figure out probabilities and stuff like that. So you can see that it looks pretty close, except instead of an a minus b times p in the inside of the parentheses, they put an ln there. There are other modifications to the logistic model where they would add some constants here or something, but that's not the Gompertz model anymore. So so what they did is just they play around with the logistics model, and then they do some sort of modification to make it fit to whatever they're dealing with. Okay, so this problem here is asking us to suppose a and b are equal to 1 in this differential equation. Then the d is autonomous again. Use a phase portrait to sketch a representative solution curves, or sketch representative solution curves for the case where p naught is bigger than e. I guess I should put this in symbols. And p naught is between 0 and e. And then suppose a is equal to 1, b is equal to negative 1. Use a new phase portrait to sketch. And then find an explicit solution to the differential equation. Which one? Oh, let's see. Phase portrait. So for the case where a, b are both equal to 1. So where's my pen? dp dt is equal to p, and then they're both equal to 1. So it would look like that. So the phase portrait, you would set this equal to 0. So either p is equal to 0 or 1 minus ln p is equal to 0. So no, do that in your head. P is equal to e. So those are your two critical points. 0 and E. And then if you do the phase portrait, we don't have to, let's not bother with anything less than 0. They just want bigger than E or between 0 and E. So if this is bigger than E, like 2E, 2 times E is bigger than E, right? We have 1 minus something that's going to be bigger than. So this is going to be a negative. So this is a positive and a negative, which is going to be a negative. So that's going to give us something that's going to go down. And then if we have a number between 0 and E, we would still get a positive for the P, and then 1 minus something like half of E or something like that. The 1 would be bigger than that number, I would guess. And so this would be positive. So I don't know if 0 is stable or semi-stable. Not, it can't be stable because the arrow is going away from 0. So it's either unstable or semi-stable, depending on what happens down here, but we don't care. We know that E is a stable equilibrium. So that's the phase portrait, and if we were to try to draw graphs, our graphs would look something like that. Now let's change our A and B. This time dP dt is equal to P times A is equal to 1, and B is equal to -1. So we have a negative times a negative. That's going to be positive. And then if we do the phase portrait for this, we set this equal to 0 again. And then we're going to get P is equal to 0, and P, if you solve for this, this would be -1, and then you take the E, so it'll be E to the negative first power. Phase portrait, 0, 1 over E is like, E is like 3.14, and so the reciprocal of that is like 1/3-ish. .3 something. So we'll put in values. Again, we'll check values. If we put in a value bigger than E to the -1, like 1, this will be positive. The P would be positive, and then this is 1 plus 1, which is also positive. So this is going to be positive. And then if we put a value that's less than E to the -1, this is still positive, but then if you put in a number that's less than E to the -1 there, it'll be ln of a point something. And if you put in your calculators, ln of 0.5 or something like that, it's actually negative. So this is negative, so this is going down. So now your E to the -1 equilibrium point is actually a repeller, unstable. So then your graphs would actually be going down. I want red. Not that you guys can see red. But if you guys print out your notes, it'll be red. I mean, if you print it out with a color printer. If you print it out in black and white printer, you still won't see red. But it's red. Okay. Oh, if you have your starting point bigger than e to the -1, then your graphs would be going up. Find an explicit solution to the differential equation subject. And now we'll differential equation with a is equal to or b equal to 1 or -1. Let's try solving for it in general, and then adjust our values for a and b. So dp dt is equal to p a minus b ln p. I have a feeling we're going to need to actually put in values for a and b here, because the integrals might look different. Oh, we'll see. So how would you solve for this? This is again separable. There's no t's in there, right? So dp over p a minus b ln p is equal to dt. Is this how would you solve for this one? Is this another partial fraction? No? What is it? What would you do? Bernardo shook his head. What would you do? How about a U-substitution? What would you let u equal to? Not just that, maybe just let u equal to the whole thing, because a is a constant, and when you take the derivative, that'll go away. And derivative of ln p is 1 over p, and 1 over p is sitting over there on the end, right? So du is equal to negative b ln, the derivative of ln p is 1 over p. So that would get rid of that p. And then dp. So we have a factor of negative 1 over b coming out. So negative 1 over b. The dp over p is gone. So that's just going to equal to du over u. Then integrate 1 over negative 1 over b ln of u is equal to t plus c. We throw in the c there. And then we'll solve for u, which is that whole thing. Is equal to, let's see, bring the b over to the other side. We're going to get negative b times t minus b times c, which is also going to be another constant. So I'll call it another plus c, but I'm going to put a sub 1. And then if I want to continue to solve for p here, I'll bring the a over to the other side. Oh, I was going to put the e here, but yeah. And then so we'll take the e of both sides. A minus b ln p is equal to, now this is e to the negative bt, and then e to the c1 is another constant. Another constant. Let's call that a, capital A. And then let's continue to solve for p. And so I'll bring the a over to the other side, and then I'll divide by b. So ln p is equal to a e to the negative bt minus a divided by negative b, and then p is going to be the exponential. E to this whole thing, a e to the minus bt minus a divided by b. Holy cow. suppose you can fiddle with this a little bit more. Oh, we didn't put in our initial value. P sub 0, P of 0 is equal to P sub 0. So we'll put P naught is equal to e to the a times e to the 0 minus a divided by negative b. And let's solve for a. Take the ln of both sides. We should have solved for a constant earlier before going this far. ln of p naught a minus a divided by. Yeah, we're just going backwards because we didn't solve for it earlier. So negative b ln p naught plus a. I don't like this. We should have solved for our constant over here somewhere instead of changing more constants and stuff. Well, in any case, depending on whether b is positive 1 or negative 1, you'll have a slightly different looking logistic function. Your logistic function will either be increasing or it would be decreasing depending on the value of b, or the sign, not just the value, but the sign, whether it's positive or negative. All right, so maybe another time solve for constant at this point. Because if you solve for a constant at that point, it'll be easier to solve for your p value. All right. There's one more that I wanted to do. And that is remember that problem in one of your homeworks from chapter 1 where there's a thing sinking or floating? Did anybody get that problem? I had a video of how to solve for that. I don't know if anybody got to that video. Do you remember? Do you know what I'm talking about? You have an object that's floating in the ocean. It's bobbing back and forth. Yeah, that was a problem way back in chapter 1. So there's a slight variation of that problem. If you take a piece of object and you drop it in the water, then it's going to start to sink, right? And then at some point, we can figure out the velocity of how fast it's sinking. And it turns out that if you have a really, really deep ocean and it's sinking, at some point it's going to maximize its velocity. It's called a terminal velocity. So let's see if we could do one of those problems. It's called that sinking feeling. All right. It says here we want to construct or come up with a differential equation for the velocity of a mass that's sinking in water that imparts some sort of resistance that's proportional to the square of the instantaneous velocity. It also exerts an upward buoyant force whose magnitude is given by the Archimedes Principle. And Archimedes Principle was back in chapter 1, I think in that section 3, 1.3. Assume the positive direction is downward. Let V be the volume of the object, rho be the weight density of water, and g is the acceleration due to gravity. Yeah, remember Archimedes Principle? What was Archimedes Principle? Maybe I don't want to do this. So, let's see. Different for the velocity. So we want a differential equation for the velocity of sinking water. So this is what you want to solve for. You're going to have a dv dt in there somewhere. What's dv dt? V is the velocity. That's going to be acceleration. So acceleration is going to come into play here, it seems like. Sinking m of mass sinking water that imparts a resistance that's proportional to the square of the instantaneous velocity. So something is equal to k times v squared. The resistance. K times v squared. What's the resistance? Also exerts an upward buoyant force whose magnitude is given by Archimedes Principle. Now I need to look that up. What's Archimedes Principle? You guys remember what it was? Something about force equals mass times acceleration. That's supposed to equal to something. Well, I have the solutions that I worked out here like last semester, so let's see. So force is mass times acceleration according to Newton's law, and upward force, the phrase upward force was used here. And since they want us to have positive going down, the upward force is actually negative F. Yeah. So the weight of the displaced water. And the weight of the displaced water is the density times the volume, right? So that's what rho times V. And we have to use capital V to distinguish from little v for velocity. So Archimedes Principle, buoyancy or upward force of the water of the barrel is equal to the weight of the water displaced, and the weight of the water is the density times the volume. We're talking about pounds and feet. And the force due to the principle is going to be Fa is equal to rho times the volume, the density times the volume. Resistance is proportional to, resistance is another force, it looks like. So the force due to resistance is K times V squared. Oh, we got that part, the resistance. And so now we have to put all these forces together. Let's see what it says here. The total force then so the total force is ma, mass times acceleration, mass times the gravity, and then there's a resistance. The resistance is a force that's pushing upward, so it's negative. And Archimedes Principle, the buoyant force, upward force, gets added on to the regular mass times acceleration. So by added on, because it's going upward, you're actually subtracting. So then your force, your total force is actually the force is equal to mass times acceleration, and then we add on the buoyant force and the resistance force. And so the acceleration is the derivative of the velocity, and then we can solve for a, or dv dt, by dividing by m. So divide by m, we just have g, and then we have these two other terms divided by m. So this is our differential equation. We have dv dt. You notice that there's no t's on the right-hand side, and so we can say that this is another autonomous differential equation. And remember that this v here is a capital V volume, which is constant, and then your variables are little v. Can't seem to circle that other little v over there. So how would you solve for this? Oh my. Yeah. 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 Yeah, it's separable, there's no t. It's just that there's a lot of these constants. If we knew these constants, then we just plug them in and make our lives a little bit easier. But if we don't know these constants, a lot of times the trick is to put all the constants together and treat them as if they were one variable. And so if, see, let me gather the g minus rho v divided by m, and maybe even divide this by m. So maybe mg. Yeah. I don't know if we can use exact. I mean, it's separable, so we could just use a separable differential equation method. Uh-oh, I have to write my little v's. I can't write little v's like that. How about if I just make the capital V like capital V? Oh, there's a K somewhere, huh? Yeah. So I think their trick is to let a group of these things equal to a constant and see what the trick was. I'll just copy this down. So this is a separable differential equation. This is your differential equation. And we can move things around to make them separable. And then here is the end result here. They say for simplicity, they want you to just consider the mg minus rho v volume divided by k. So we're going to let that equal to a squared so that we can integrate this thing easily. Yeah. Because writing it as a squared dv, I guess they say alpha squared minus v squared is equal to k over m dt. Integrating this is easier than it was if it was just a minus v. Integrating this, you can use partial fractions, because this would be the difference of two squares. So it'll be alpha minus v and alpha plus v, which is easier to integrate, I think. Yeah, apparently. So the thing is that we're going to be carrying this big constant around whenever we're working this out. So if that is just a constant, then just replace it with another constant. Kind of like what happens when we do that exponential function, and then e to the c is just a constant. We're calling it a. So, wow, you guys better brush up on your partial fractions for the test. All right, well, we're almost out of time, so I'm just going to copy the rest of the solutions since I already did it. I think at some point I went from alpha to a. We ran out of space. All right, so we got this nice complicated looking solution, and they want us to find the limiting factor. The limiting factor is a factor where you take your t and let it go off to infinity, and then if you take your t and let it go off to infinity, there might be some L'Hopital's rule going on there to come up with the answer. All right, so look over your 3.1 and 3.2 and make sure you know how to translate those things into differential equations, and then we'll practice solving for them. Okay, so next time we'll review. Good luck. Do your homework. Time to go.